good morning, everyone. Thanks for having me here. I appreciate it. Thanks for the introductions. As Sunita said, my name's Powis. I'm a PhD candidate at Princeton University, and I do a lot of my work in collaboration with the Princeton Plasma Physics Laboratory, particularly in developing software for modeling kinetic low temperature, simulations of kinetic low temperature plasmas. And obviously, unsurprisingly, perhaps we're looking at accelerating these simulations on the GPU using a paradigm such as OpenACC. The first slide here is just really talking about, well, what is a low temperature plasma? I'm sure many of you, when you've heard of plasma applications, you've heard of such things as fusion energy, perhaps plasma wake field accelerators, lots of really exciting technologies. But actually in industry, some of the most ubiquitous uses of plasma are in what we call the low temperature regime. So perhaps one you might be most familiar with is materials processing. And in particular, the lower picture here actually shows what's called a plasma reactor, which is where you'll place silicon wafers and those will be etched to produce microprocessors. Extremely relevant, obviously, to all of our work. And so, like most plasmas, low-temperature plasmas exhibit complex dynamical phenomena, and that includes collective behavior, long and short-range forces, but particularly in the low-temperature regime, we have non-equilibrium and kinetic species. And so non-equilibrium, in this case, we're referring to electron temperatures on the order of 1 to 10 electron volts. That's low temperature for a plasma, but our ion species can actually be at room temperature. We also have to consider a strong effect of interfaces between solids and liquids, as well as chemical and biological interactions. So it's quite an interesting regime of physics. Our application is called, very creatively, the Low Temperature Plasma Particle and Cell Code, so LTP-PIC for short. And really what we're trying to do here is enable laboratory science as well as industrial design of low temperature plasma devices. So the impetus to model real industrial systems which incorporate kinetic plasma, so that's resolving a 6-dimensional phase space, puts for us a huge impetus on performance. But at the same time, we also want to develop an application that provides open access to students and researchers, as well as obviously cater to our industry partners. And that puts a big impetus on portability. So I'm sure you can see where this is going. We really thought that when moving to GPU frameworks, which are required for performance, getting portability for us, one of the best options was actually to go with OpenACC. And that's what drove us to make that decision as opposed to using alternative frameworks. So just really briefly here, the code design, it's a 2-dimensional and then 3-dimensional in velocity space particle and cell code, as I said, for modeling low temperature plasmas. So PIC, as it's colloquially known, is a mixed Eulerian-Lagrangian framework. And the idea here is that the Lagrangian sense of it somewhat reduces the cost of discretizing the full 6D phase space, in the sense that you don't fully discretize on a grid that velocity space. You actually sample it through a Monte Carlo method of sampling that distribution function. So in the Lagrangian sense, we have these particles or macro particles, which are initially set up in phase space, and their density, or specifically their charge density, is interpolated onto an Eulerian grid. And on that grid, we actually solve Poisson's equation. In the low temperature regime, we can usually assume it's an electrostatic plasma. And so Poisson's equation here is the way to go. And then we compute the electric field on the grid and interpolate these quantities back to the particles. And then we evolve those particles. And of course, here we also can incorporate collision algorithms, also a Monte Carlo process in this case. So this code, with all of our performance requirements in mind, this code is designed from the ground up for scalability. And before we took part in this recent GPU hackathon, this was mostly via MPI and OpenMP. And I want to mention that we do couple with a linear algebra package known as Hyper, which we've had really great experiences with. And I'll talk more about that specific package in a few minutes. So a couple of months ago, in June, we took part in the 2020 Princeton GPU Hackathon. And these are the members of the team here who participated, but also a huge thank you to Stefan Etier from PVPL, as well as Matthew Colgrove and Mozgan Chime from NVIDIA for their support, as well as the support of the Oak Ridge National Laboratory. We had a really excellent and as I hope you'll see, successful time with this process. So now what I'm going to do is I'm just going to talk through the algorithm and the different portions of it and the successes that we had, basically accelerating them using OpenACC. And again, feel free to target me with specific questions after this talk if you want to know more about this. So what were we trying to accelerate? Nearly the entire code. And so we have this setup phase at the beginning. It's effectively an initial value problem with time stepping. So we have this setup phase at the beginning, and then we load all of our large memory structures onto the GPU. And all of that time stepping is performed on the GPU. Now, some functions do remain on the CPU. We have an option for the field solver to be performed on the CPU, and I'll talk about why that's the case in a second. Communication, obviously, we have CUDA-aware MPI working, but still we have some communication, inter-node communication going through the CPU, and diagnostics, obviously, are still, most of that's still being performed on the CPU. So going through these different stages of the algorithm now, in terms of the particle push, this is actually embarrassingly parallel. We just put some OpenACC pragmas around it, and we saw very rapidly 100 times speed up compared to just MPI. And so this was a large speed up, but completely expected. The next part of the algorithm we explored was this interpolation from this, Lagrangian particles onto the Eulerian grid. And this is nearly embarrassingly parallel, except there's a couple of points here, a couple of caveats. Firstly, this requires non-uniform random memory access. So what I'm saying here is that the way the grid is stored contiguously in memory is counting these cells in order, along the row and then along the columns, etc., etc. And the way the particles are stored is contiguously as a list of particles. But the way you access the grid or the particles themselves is effectively random with respect to one another. So this, in terms of loading large pieces of memory contiguously and predictably, this is kind of, can be a huge bottleneck. And the other factor is that when we're interpolating those particles onto the grid itself, you need to have atomic memory access in order to avoid those, to ensure that is occurring correctly. But actually, we weren't really sure what to expect speeding up this algorithm, and we actually saw a speed up between 100 to 200 times, which was definitely better than we expected. And we haven't dug into why this is the case, but I'm assuming it's down to low memory latency in some respects. So that was a really interesting outcome for us. Now things get a little more interesting for solving Poisson's equation. So the challenge here is Poisson is an elliptical PDE, and this therefore requires a global solve and requires global communication effectively between all of the cells. And particularly on CPUs, we've seen, state-of-the-art is using something like people often use algebraic multigrid algorithms, but we're using a structured grid, so we relied on geometric multigrid algorithms to get a little bit of extra speed up with the knowledge of that structure. And as I said, we use the Hyper package, which runs on CPUs and also has a GPU implementation, but with the caveat that this is a work in progress. So what did we see with this? We found that the performance of Hyper was really good on a single GPU, if the problem is large enough. So this figure here just shows, so we did a scaling test on a 2D grid. So this is the number of grids on a given, a number of cells on a given edge. So this is, the number of cells is the square of this in the entire grid, basically. And then the solve time here is it's the solve time divided by the number of cells. So you see here that the GPU actually performs really fantastically when you go to large grids, and it really starts to take off when compared to the CPU. But for our application, we're usually around about in this range here on a given single node or single GPU. So we didn't really see that much of a performance gain from this. The other thing is we actually kind of saw poor scalability when we were going to, in a weak scaling sense, when we were going to multiple GPUs. And I think that this is kind of an open challenge, if I understand it correctly, for elliptical solvers, that getting them to scale really well across multiple GPUs is still a work in progress, although I'm very happy to hear about solvers that are working well in that sense. The next challenge, and this is something we're still in the process of implementing, is these collision models. And collisions in PIC codes are a Monte Carlo process. And in this case, we require on the order of trillions or trillions of high quality random numbers. And we looked at different approaches for doing this. So, a particular standard approach would be generate random numbers on the CPU and port them over to the GPU. But because we need so many random numbers and on the fly, we really did not want to go through this process. So ideally, we want to produce random numbers on the GPU. And again, coming back to the whole purpose of OpenACC, we want to do this in a portable way. So not using something like cuRAND, for example. So one of our researchers, Johan Carlson, really suggested that perhaps the most scalable solution is to store a pseudo-random number generator state with each of the particles itself. And then we can generate random numbers with OpenACC at the thread level on the fly. The challenge with that was that a lot of the state-of-the-art random number generators, for example, the Mersing Twister, have states on the order of kilobytes, and we just can't afford to shunt those states around when we're reordering memory or moving particles across different processes. So he actually found that using block ciphers, based on the data encryption standard, so this is blockchain technology, can actually generate random numbers from a 7-byte state. And this is actually perfectly acceptable for us because the state of a given phase space of a single particle is on the order of 20 to 30 bytes, and so this is not a significant overhead. We did see a slight increase in random number generation time for this technique, but in terms of the scalability that it gives us, this is certainly tolerable. It also passes all of the small crush tests. This is a pretty standard suite of random number tests. And so we were quite happy with that. And we're in the process of now porting this pseudo-random number generator to the GPU via OpenACC, and then we're gonna use that in building our collision algorithm. So that's what we attacked in the algorithms. Let me just talk a bit, about what people want to see usually is the performance gain that we had. So we firstly and most importantly, obviously benchmark your code. After all these changes, we benchmarked it against a known simulation setup, and we saw everything we expected. It was benchmarked successfully. And then in terms of performance, we were looking at running on PPPL and Princeton's Traverse supercomputer. So this is a Power 9 system with NVIDIA Volta 100 GPUs. And the performance comparison was just run on one node, a single node, with a typical load that we would expect from a single node in our simulations. So really what we're doing here is each node here has 4 GPUs. So the main comparison I initially made was between 4 MPI tasks acting on their own and 4 MPI tasks plus 4 GPUs. But it doesn't seem really fair to compare that alone when we have the rest of these 32 CPUs on a node, which wouldn't really, well, 28 of them wouldn't be doing anything. So we also compared it against using the whole 32 CPUs. And we see really a remarkable speed up. I mean, so, in comparison here, just for the 4 MPI tasks, it takes us around a second to perform a single time step, whereas it's around 30 milliseconds on, combining that with the GPU. And unsurprisingly, the biggest speed ups are really with the particle push and here an interpolation. But to make this more clear, I'll show you the speed up performance. And again, here, the particle push and interpolation are off the charts. particle boundary conditions, there's some communication in here from moving particles between different processes that causes a bit of a slowdown. And other aspects of MPI communication are encompassed here. Other here includes diagnostics, and the field solver here is actually only being performed on the CPU in this case, so there's not really a significant speed up. But in comparison, we get a 30 times speed up using the GPUs compared to just the 4 MPI tasks, and around a 10 to 15 times speed up compared to utilizing all of the CPUs on a given node. So we were very happy with that performance gain. This is a simple weak scaling test, obviously scaling the size of the problem with the number of GPUs, and this is very indicative of what we expect and what we see actually when we're running on CPUs. So we were happy with this also, but herein lies the problem that we're tackling now. When we were running on CPUs, a lot of our application was completely bound by these particle routines. So if you can see that here, this is interpolation, this is the particle push. But these are highly parallel on the GPU, and when we move to using CPU, GPU with OpenACC, we become limited actually by the field solver, which we haven't yet been able to find a way around or found a good GPU algorithm to handle this. So this is where we are at now. This is the problem that we're facing as we seek to achieve better performance and better speed ups going forward. But in terms of portability, similarly, we had great success. So I'm not going to go through all the different frameworks, but we have our code running on Power 9 architectures, on Intel Broadwell chips, as well as other Intel and AMD chips at PPPL, and as well as on our local machines. So one caveat here is that we're still maintaining OpenMP operability so that we can compile with Intel compilers, and this is pretty important for one of our machines, Perseus. So this adds a little bit of verbosity to the code. But otherwise, OpenACC has actually allowed us to maintain a single code base and interoperability, which we honestly don't believe we could with any other approach in such a straightforward way. So just to draw some conclusions here, here's a big sort of wall of text, but this is really summarizing the lessons that we learned from this process. And honestly, we were really amazed with how easy it was to use OpenACC. In most cases, you could just either replace OpenMP flags or put OpenACC flags in line with OpenMP. There were some inevitable learning curves dealing with memory management, which we actually chose to do explicitly, but these can be quite readily overcome. GPUs are extremely powerful. Myself and some people in our group were a little bit uncertain about what kind of performance gains we would see and whether it was actually worth making the effort. And OpenACC really opened that up for us and demonstrated that there's so much power to get from the GPU. And we were pretty impressed with what we think is, a benefit from low memory latency, as we saw in these interpolation algorithms. One of the challenges we're facing is the portability for random number generators on the GPU. And this was not immediately straightforward for how to do this with OpenACC. And I think an ongoing problem for scalable, for GPUs in general, is scalable linear algebra solvers or elliptical PDEs, or sparse linear solvers, effectively. So just the final few points I want to make is sort of our OpenACC and GPU wish list. I think the first one is probably pretty standard among many users, is further interoperability with OpenMP and with other compilers, with OpenACC. And the way I understand it from my admittedly limited experience is that these two standards are coming together in some sense. So we'd love to obviously see OpenACC working on Intel compilers, effectively to the point where these things become, the same. Perhaps less expected is, or a less regular suggestion is we'd actually love to see the potential for pseudo-random number generators being built into OpenACC in some way. And I think that would potentially have many uses for many applications on the CPU and the GPU. And then our general big picture wish list, which isn't necessarily specific to OpenACC, is that for good quality elliptical solvers. So with that, I'll thank you for listening.